Welcome. This is lecture 57. In this lecture, we look at Koszul complexes, how they are constructed using a mapping cone. We'll start with looking at a mapping cone, then we'll define Koszul complexes as a mapping cone. Okay, so what we will quickly review how we define complexes, and then we will now define maps between complexes, and then we will talk about mapping cones, and then, so that's the plan for this lecture. Okay. So recall that a complex of R modules is a sequence of R modules and R module homomorphisms, so M dot, okay. So it's a sequence which goes M0, then M1 maps to M0, M2 maps to M1, okay. And sometimes we will have to refer to the maps, so we will just label them. So, and why is it a complex? So that image of mu I, so the map from mi to mi minus 1, its image is in the kernel of the next map, kernel of mu I minus 1. Okay. So, or equivalently, composition of two consecutive maps is 0. Remember, the composition is mu I first and then mu I minus 1. Okay, so it's 0. And in principle, one does not have to have a 0 here. You could go even to infinity on the right side, but the complexes that we will consider in this course will always end somewhere and then it's 0 afterwards. Okay, so we will just consider only such complexes. Okay. The homology of a complex is the ith homology, Hi, is the kernel of mu I, which is the map going from mi, modulo the image of the previous map, mu I plus 1. Okay. So remember that image of mu I plus 1 is always inside the kernel of mu I. So the quotient, the module, is called the homology of this complex, the ith homology of this complex. Okay. And we can, at this point, we can think of the last map from mu M0 to 0, I mean, you can think of it as the map mu0 and as a 0 map, okay? And hence H0 of this complex would be kernel of mu0, this should be mu0, mod, so kernel of mu0 is all of M0 and kernel of mu1 is just, an image of mu1 is just the image of mu1. So M0 mod the image of mu1, which is what we call the co-kernel of mu1. So remember that the H0 of such a complex is a co-kernel of this last map, M1 to M0. If we have two complexes, okay, F where we denote the maps by small f, and G where we denote the maps by small g, if they are complexes as above, so ending at some 0 and then 0 modules of 0 afterwards, a map of complexes is a collection of R module homomorphism from each Fi to corresponding Gi. So Fi to Gi, Fi minus 1 to Gi minus 1, and so on both sides. Okay, such that the following diagram commutes. Okay. What does that mean to say diagram commutes? It means that between any pair of points, all the arrows going from one to the other are give the same function. So in this case, there's only one to check, which is from Fi to Gi minus 1. There are two paths, Fi to Fi minus 1 to Gi minus 1 and Fi to Gi minus 1. So along the sides of this rectangle, one gets two different paths and those two functions agree. So in other words, Gi alpha I, which is the path down first and then to the right, that is the same as right first and then down, alpha I minus 1 Fi. So these two composites are the same. That's what diagram commutes means, and that's what it means in this context of a map of complexes. Okay. So if you have a map of complexes, then it induces a map in homology, that is a map alpha from F to G induces a map which we will denote by Hi of alpha from the ith homology of F to the ith homology of G. Okay, so so these proofs are done using what is called a diagram chasing. So we will just do the diagram chasing on this diagram itself. Okay, so we need to find an element, we need to look for elements in the kernel here. that is kernel of Fi mod image of Fi plus 1. Okay. And we need to get them to an element in kernel of Gi mod image of Gi plus 1. So from the kernel in the top row at Fi to the homology of the bottom row that is inside Gi. Okay. So we'll do this by doing what is called a diagram chasing. So let's pick an A in kernel of Fi. Okay. Remember, elements of homology are kernel mod image. So they are represented by the residue classes of elements of the kernel going modulo images of the previous image, the submodule image of the previous map. So we'll just take an element in the kernel. Okay. So kernel of Fi, so it's in kernel, so it just means that A goes to the 0. So the things that I mark in red are the elements that we pick, and as we'll see how the elements progress in this diagram chase. Okay. So A goes to 0, that's what we have written, Fi of A is 0. Now define B to be the image of A under alpha I. Okay. Now because the diagram commutes, B must go to 0 in Gi minus 1. So start from A, it goes to, chose A inside we chose A inside kernel of Fi, so it went to 0 here and then came to 0 here. So along top and right, we get 0 inside this Gi minus 1. Therefore, on the bottom, left and bottom also one should get this. So Bi must be in the kernel of Gi. B must be in the kernel of Gi. Okay. So in other words, what we just observe is that alpha I maps the kernel of Fi inside the kernel of Gi. Okay. So we can think of this as a map alpha I restricted to kernel of Fi. Okay. Now let's check what happens under this map to image of Fi minus 1. Okay. Remember that image of Fi minus 1 is inside the kernel of Fi. Okay. So under this map, what would happen to image of Fi minus 1? Okay. So now let's assume that A is in the image of the previous map. Okay. So in other words, A is Fi plus 1 of some A1. So okay, this A is the image of this A1. Okay. Then because of the commutativity of the diagram, one can immediately see that this B, okay, which is also Gi plus 1 applied to alpha I plus 1 of A1. In other words, B is in the image of Gi plus 1. So if A is in the image of this map, the top row map, then so is this B. That's the conclusion. In other words, under this map, alpha I restricted to this kernel, image of Fi goes inside image of Fi plus 1 goes inside the image of Gi plus 1. Okay. So now what do we have? We have a map from the kernel in the top row to the kernel in the bottom row, under which the image in the top row goes inside the image of the bottom row. Okay, when we so now this gives a map from kernel mod image on the top row to kernel mod image in the bottom row, and that's exactly what Hi of F to Hi of G is. So that's the end of the proof. So the conclusion is that any map of complexes through this diagram chasing gives a map in homology. Okay, so now we want to look at this thing called mapping cones, which is a way. Okay, so here is a motivation or our aim. So we have given a map of complexes. So we have these maps now. Okay. We would like to fit them into some exact sequence like this. So this is the map. This is a map in homology at the ith level. So this is at the ith level. Okay. This is the map in homology at the I minus 1th level, and we would like to put them in such a long exact sequence because it would help us conclude various things. So this is again a post facto justification. We would like to put them like this in a nice way. And what do we exactly mean by nicely? So we would like to describe these Mi in such a way that we can say something about the maps alpha I, or they're somehow constructed in some natural way. Okay. There's no definition as to what exactly we should, what exactly the natural way is, but we will describe one such thing called mapping cones. Okay. So the aim is to understand the map of, the induced map in homology, how does it fit together? What is its kernel and co-kernel? Okay, so that these things would be clarified if you put them in a nice exact sequence like this. So the aim is to construct such a nice exact sequence. Okay. So this is what we start with. So we are now going to describe the construction of the mapping cone. We have a complex F on the top row, complex G in the bottom row, and I have drawn it from the rightmost end, where F0 to G0, and then to its right, these are all 0 modules. Okay. So we have a map like this. Okay. So now we would like to describe what is called the mapping cone of this map of complexes. Okay. So here is the thing. Well, let's see how this was constructed. So now let's look at G0 here. Let's look at G0. Okay. There are two maps coming from to G0. Okay. One from F0 and one from G1. Okay. So F0 and G1 map to G0. And alpha 0, F0 to G0 is alpha 0 and G1 to G0 is G1. So in this mapping cone, we put this here, G1 plus F0, and from the first factor we use the map G1. For the second factor, which is F0, we use alpha 0. Okay, so that just came directly from this. Okay, so here is here is G0. We just map to all the modules that map into this, which is from the F complex and the G complex, one module each. So that's what we have here. Okay, so from G1 to G0 is G1, the map G1, and F0 to G0 is alpha 0. Now we have now in the second position of this complex, the new complex, we have G1 plus F0. So the things are on this diagonal like this. Okay, G1 plus F0, and there are two modules behind them which map to these. That is, there is G2, and then there is F1. Okay. F1 maps to G1 and F0. Okay. So the F1 maps to F0 through the map little f1, to G1 through the map alpha 1, and G2 maps to G1 through the map G2, little g2. Okay. So let's put that thing together here. So this is written as like a matrix, but it's not exactly a matrix. It is just a convenient way of writing because it's a map from a direct sum. So G2 direct sum G1, G2 direct sum F1 to G1 direct sum F0. From the first part here to the first part here, which is G2 to G1, we have a map G2. Then from the first part here to F0, the second part here, there is no map. So it is 0. From F1, which is the second part here, to the first summand, which is G1, there is a map alpha 1. So we have this. And from F1 to F0, there is a map little f1, but we just put a minus sign, and we'll see why this is needed. Okay, so we just put a minus. The only thing you keep in mind is that there's a minus sign there. Okay. Similarly, from we have G2 direct sum F1. The map would be from G3 direct sum F2, and from G3 direct sum F2, G3 to G2 there is a G3 map, G3 to F1 there is no map, F2 to G2 there is an alpha 2, and F2 to F1 we put we have a map F2, but we use that with a minus sign. Okay. So now we have we have this, and the point is that, so this I've just copied it. Okay. This is the same complex that we just described in the previous page. The point is that this is a complex. Why? So let's check this. So which means we should check that this map here, the square, the G2 to G2 direct sum F1 to G1 direct sum F0, this map here to the next map, the composite should be 0. So remember, the maps are applied in the opposite order. This is the one that's applied first, and then this 2 by 1, this 1 by 2 looking matrix. So this is the composition, and one can immediately check that because of the diagram commutes, G1 alpha 1 equals alpha 0 F1, and because we introduced a minus sign, they cancel each other and we get 0 map. And similarly here also. Okay, the diagram commutes, so G2 alpha 2 equals alpha 1 F2, but we introduced a minus sign precisely to cancel this, and so we get 0 in this part, and G2 G3 is anyway 0 because it's a complex, and F1 F2 is also 0 because it's a complex, and so on to the left. Okay, so except at the rightmost place where one has to multiply a matrix like this. Rest of it is all like these 2 by 2. These are not matrices, but two summands on both from each one of those complexes. So we get this. So this is a complex. Okay, so now we will need to work with this complex a little bit. We will write delta I for these maps. So this is G0 here. This is C0. This thing here is C1. G2 direct sum F1 is C2. So the index of G, the subscript for G is the one which describes the subscript for C. Okay, so this is how. So the map we describe as delta I. So now what we have constructed, from what we have constructed, we have what is called a short exact sequence of complexes. Okay, so I won't define it. I will just describe these things in this context, but we will do an exercise which describes it in full generality. Okay. So what exactly do we mean? Okay, what are these maps? First of all, the vertical maps, the vertical maps little g and vertical maps fi, and here minus fi, they were given to us. These delta i's were constructed as in the previous pages. Okay, so now we are to describe the horizontal maps. This is the inclusion in the first summand. Okay. Remember, Ci is Gi direct sum Fi minus 1. So the inclusion from Gi to Ci is the inclusion as the first summand, and Ci to Fi minus 1 is the projection to the second summand. Okay, so therefore the rows are exact. Okay, so that's what here we mean. So this is important. Rows are exact, and all the squares in these commute. Okay, that's because, in other words, way of saying is that, we'll see it in a minute. Okay. Rows commute, one can check explicitly because the first factor, if you go here and apply delta, it is the same thing as applying G, because nothing happens to the second, and so so one can write down from those matrices and check that all the squares commute. Now, here's a general fact about short exact sequence of complexes. So we'll make a proper definition of this, etc., and prove this fact in this generality in the exercises. Okay, so for every short exact sequence of complexes, there is an exact sequence in homology. So ith homology here, ith homology here, ith homology here. So hi. Then I minus 1 here, I minus 1 here, I minus 1 here. Those 3 things, and then I minus 2, 3 things, and so on. Okay, so this is a general fact. We will so we will prove this just for this mapping cone case explicitly. Okay, general case, as I said, would be an exercise. Okay, so the squares here commute says that if you look at the vertical arrows, the collection form the complex G, and the middle arrows here, vertical things, form the complex C, and the arrows commute is the same thing as saying the left from the complex G to the complex C is a map of complexes. So we get this we observed earlier, there is a map of homology. From Hi of G to Hi of C, there is a natural map which came from the map of complexes. Okay, now just observe that the last column is not the complex F, but there is a minor modification, which is that its indices have been shifted by 1. At the ith position of the new complex, we have Fi minus 1, and the maps are multiplied by minus 1. So there's a shift in the indices and a multiplication by minus 1 in the maps. Okay, so we'll call this new complex F prime, just a notation. Okay, the observation that we need to make is Hi of F prime is Hi minus 1 of F. The kernel and image don't change if you multiply by minus 1, and all that we have done while computing homology, only thing that we have done is changing the indices. So what homology we would have obtained at I minus 1 position, if we are treating it as f, we would now get it at ith position. Okay. So now C to f prime is a map of complexes, and so we get a map hi of C to hi of f prime, but remember that is hi minus 1 of f for every I. Okay, so then one needs to check. Okay, so this is just a sort of preliminary discussion. One has to check that if you take this map, hi of G to hi of C to hi of f prime, it is exact at the middle part, which is hi of C. That we won't describe. It will come from the general principle about short exact sequence of complexes giving long exact sequence of homology. So we won't explicitly check in this lecture. But let's see how the mapping, what specific thing happens in the mapping code. Okay, so I have left some gaps to fill in elements here. We're going to do a diagram chase. Okay, so now, let's go back. Composing these two, hi of G to hi of C to hi of f prime, okay, we get something like this. Okay, the middle part is C, left one is G, and right side is f prime. So we get something like this. What we want is the switch from the ith stage to I minus 1 stage. So hi of f prime to hi minus 1 of G. So it is this map that here that we are trying to construct in the what we will describe now. Okay. So yeah. So we need something to go from this homology here. Remember, this fi is f prime of I minus 1. Sorry, f prime of I plus 1. So from this point to this, the homology of the rightmost complex at this point, to the homology of the leftmost complex at this point. Okay, that's what we will need to construct. Okay, so let's take a B. So we'll do a diagram chase like earlier. So let's take a B, which is the kernel of fi. Kernel of fi is same thing as kernel of minus fi. So this B here goes to 0. Now lift it to any a comma b. So remember, ci plus 1 is the direct sum of these two things. Okay. So lift it to any a comma a plus b, a comma b, where a is from gi plus 1 and b is whatever. So it doesn't matter what a is. Lift it here. Let's apply delta. Let's come down to this map. Well, if you come down to this map, G gets applied to A because A came from this. Alpha gets applied to B because alpha came from here. B came from here. Okay. And then for the second command, the second component, F gets applied to B. Okay. So what we have is Gi plus 1 applied to A plus alpha I applied to B. So I have just, in this thing I have just to conserve some space, I have just called it Ga plus alpha B. But usually after a while, keeping track of these indices, unless there is a pressing need for it, one understands that this is after applying the correct G in the correct degree. Okay. So this is Ga plus C. So we get an element here. And remember that the map from, in the second factor, the map is B going to f of B, but B is in the kernel of f, so it is 0. Okay. So one has this. Okay. In other words, this element here came from Gi. Okay, so this is the element that we, okay. So from here, we lifted arbitrarily, then we applied this map, and then we got an element inside G. Okay. If you apply the G map to this Ga plus alpha B, we would get 0 because Gi, so this one can just check, this is just a map, two consecutive maps in a complex. And for this factor, one has to use that the diagram commutes. Gi alpha I B is some alpha FB, but FB is 0, so one gets 0 here. So in other words, what we have is, we have a well-defined map from the kernel of Fi to the homology at Gi, not to the kernel, because the actual map depends on the choice of A. Okay, so there is no well-defined map from kernel of Fi to kernel of Gi. There is a map to kernel of Gi mod the image of mod the image of G. So remember, okay, so one has to make it a well-defined map, R linear map, one has to go modulo the image of Gi. So this is the map, kernel of Fi to Hi of G, where B goes to alpha IB. Okay, so this is, okay, and this map does not depend on the choice of A, because whatever, if you chose an A prime here, if you do the same thing calculation here, you will get a different element here, but that different element will be inside the image of Gi plus 1. So in the homology, it will be the same element. Okay. So one has to check that this is R linear, etc., which it is. Okay. So now we get a map from kernel of Fi to homology of alpha I, which came through the map of complexes alpha. Okay. It is an element in the kernel to which the map alpha I is applied. Okay. So this is what we have. Now, what we had wanted was from homology of F to homology of G. So, in order to do this, we need to understand what happens to the image of the previous map. Okay, so now suppose that B is actually the image of the previous map. So, Fi plus 1 minus Fi plus 1 of B prime. Okay. Then one can just immediately check this. Alpha I of B is minus alpha I Fi plus, so this is just substituting this B prime. But alpha I Fi plus 1 is, using that thing here. So now one immediately sees that if B is in the image of this, then alpha IB is in the image of Gi plus 1. Okay. In other words, the image of Fi plus 1 inside this kernel here, okay, goes image of Fi plus 1 inside the kernel here goes to the image of this thing. So inside the homology it is 0. So hence we get a map from Hi of F to Hi of G given by alpha. Remember, this is how the map in homology was defined. Kernel goes to Z. If you have an element B in the kernel, the map takes the class of B to the class of alpha IB, and that's exactly what this map does. And now, so with this we have established, so let's just summarize. Given alpha map of complexes, we have an exact sequence. Okay, so let's just make sure we get this thing. So this is Fi, homology here is Hi of F, homology here is Hi of G. So the map that we have constructed is from here to here. Okay, and then we have this. So Hi plus 1 of C to Hi of F to Hi of G to Hi of C, and then so on. Okay. So this is how this thing comes. Now we come to this point of defining Koszul complexes. So we have a ring and some T elements in R. The Koszul complex on F1, a single element, is the complex in which we put this at the first position and this at the 0th position, multiplication by F1. Okay. Inductively, let's assume that up to for I elements we have defined it. Okay. Now multiplication by Fi plus 1 gives a map of complexes, just a map of complexes, and the Koszul complex on F1 through Fi plus 1 is a mapping cone of the above map of complexes. Okay. So if there are two, and we will see in Macaulay how these things are constructed. So now we define a map from rank 1 R module to rank 1 R module, multiplication by X. And we ask, is homogeneous 0, 0? And it says it's false. Okay. And the reason is, both generators in both these modules, basis elements have degree 0, and hence multiplication by X won't preserve degree. It's just saying it's not a homogeneous map. So we can make it homogeneous by giving degrees like this. So this is a free module of rank 1 free module where a basis element has degree 0. This is R minus 1. So there is a basis in which the element has generator has degree 1, okay, and multiplication by X now preserves degree. Okay. Yeah, so let's just ask what these things are. R0 just a R module free, R minus 1 is R module free, degrees is 1, the generator degree is 1. We ask Macaulay to construct the Koszul complex. So Koszul complex is asked for a map. So Koszul of phi of x was that multiplication by x. So we call it kx. Okay. Then we ask, so this one, these three commands will tell you the 0th element in the complex, the first element, the module in the complex, and the differentials in the complex, the maps in the complex. Okay, so it says, so it showed us this complex 0 and 1. It says the chain complex. First module, I mean 0th module here is R1 free. Second module is R1 free, but the generator degree is 1. Okay, and if you ask for its map, it says this is the map. Okay, so now we define similarly phi y, okay, and we ask for Koszul, we can ask for the Koszul complex. Okay. So now mapping cones. So now we need to shift, we need multiplication by y to be homogeneous. Okay. So we can't use kx itself, we need to change its degrees. Okay. Remember, if multiplication by y has to be homogeneous, then it has to come from r minus 1 to r0. Okay. So we take kx itself, but when in order to be able to multiply by y, we shift the degree and call it. So the star r minus 1, okay, it has a correct interpretation in terms of tensor products, but for us we will just treat it as shifting degrees. Okay. So now we ask for kx1. So the 0th module now is in degree 1, and the first module is in degree 2. Generator is in degree 2. And the map is still multiplication by. And as I said, for us, kx star r to the minus 1 is just a way to change the degrees of the basis element. Okay, correct. Yeah, so just one more. The 1 here that precedes x says that the target has degree 1, so the source has degree 2. So that's just, I'm just saying. Now let's try, so now this extend is a function which tries to extend a matrix as a map of complexes. So we want a map from kx1 to kx, multiplication by y, that's what this one does. Okay, and we ask, okay, so now it's a map of complexes, in both factors it's multiplication by y. Okay, and then we ask Macaulay to construct its cone, and we call the cone kxy. Okay, so if you ask for kxy, now it's cone of 2 elements, and one can inductively prove that the matrices in the modules in the Koszul complex are free modules. 0th module is just 0. First module is 2 copies. Remember, it's on the diagonal. There are 2 elements, and after that, both complexes end. So there's only one in the next stage. Okay, and so here it is degree 0. The first module is 2:1, which means 2 generators of degree 1, and the second one, the final one, is degree 2. Okay. So that's those are the commands, and then we ask for the maps, and these are the maps. Okay. So when we work out the chain complex maps using the mapping cone, one can see that these are the maps. Okay. We can ask, here we also ask for its homology, and prune is to minimize the number of generators. And okay. So when you ask for its homology, it said it's a co-kernel of xy. The middle one, it said it's a subquotient of this. Okay, so in other words, it's a submodule generated by this modulo the image of this one. And when we ask for it to prune, the first homology is 0. Okay, so one gets only one element. And let's just quickly look at it for 3 elements. Okay, so now we do the same thing. We take the complex kxy and then shift its degrees by 1. Okay, so all that we have done is just shift its degrees. Okay, now so the new complex was called kxy1. So get a map from kxy1 to kxy multiplication by z, then ask for its cone. Okay, and look at its so this is the extension. So this is shifted, and everywhere it's multiplication by z. Okay, so here there are 2 factors, so it's a 2 by 2 matrix. Okay, and then we ask for its cone, so we get something like this with 1, 3, 3, 1, and we ask for its maps This is what we get. If you did this by hand, we would get, I mean, depending on the sign conventions, we might get a slightly different, with different signs, but it would be isomorphic to this. Okay. And so we can ask, so this is what we constructed by Kohn. We could have just asked Macaulay to construct the Koszul complex from the map to, so the generator here is in degree 0, 3 generators of degree -1, and they get mapped to x times this, y times this, and z times this. Okay. We ask for its Koszul complex. We ask for its chain complex. So this sign, I mean, it's a convention of how one is taking the tensor product. So this matrix is almost the same as this matrix, except for some changes in sign. Okay. But that's okay. And then finally, one gets this. Yeah, that's the end of this lecture.